Hey, welcome to Introducing Differential Calculus. Hey, what are these two old guys here with the wigs, hey, nice wig, mate, doing? They're back in the 17th, 18th century, and they're attributed with discovering differential calculus, and they were working independently and looking at the same sort of maths. Hey, this is going to be good. These two guys actually developed differential calculus, and you can be proud that you're now studying that. If you say to people, hey, I'm doing calculus, they'll say, wow. It isn't that hard, though. It's an interesting area of mathematics, so let's go and develop it and see what you think. So come on down now to what they were doing. I think there are two ways of describing what these guys were doing. First of all, finding the slopes of tangents to curves. Okay, and that was more Leibniz approach, and then Newton had a sort of a more practical approach, I think, finding the rate of change of one variable with respect to the other, and we're going to look at what Newton did, and of course the maths is the same from both guys' points of view, but finding the rate of change of one variable with respect to the other, let's have a look at that and why that is important, because that's a mouthful, finding the rate of change of one variable. What? Okay, let's see what it does mean in terms of what Newton was doing. So come down and have a look. You know Newton was a physicist, very, very wrapped up in motion problems, Newton's laws of motion, as you might remember, gravitational law as well, but laws of motion, very, very important. So he was working with plotting distances travelled by a body against time. And we've done some of this in junior maths. And so if you plot up here distance in kilometres and time in hours, just watch the labelling and the scale of any graphs you draw, then you might have plotted the body and you find it at point P after 1 hour, it's gone 280 kilometres, and then at Q after 3 hours, it's gone 440. Can you work out the velocity of this body? Yeah, well, it's a change in, so here's delta S. Now, what does that mean? That implies in mathematics change in. The delta sign there, I haven't drawn a very good one. Delta S. This is a Greek capital delta. Okay, and we use it to mean change in. So this is like your old junior maths y step over x step, isn't it? Distance travelled over time taken, if you like. So the slope of this line is, let's use this delta notation, delta y on delta x, change in y over change in x, which is here change in distance with time, which is going to be the velocity of the body. Now this, no matter what 2 points you use, let's use another 2 points on this line. Because it's a straight line, you'll get a constant slope. So velocity will be constant in a plot like this, because every 2 points along the line, whatever 2 points you take, will have the same delta y on delta s, or change in displacement with time. Do you get it? That's important, because that's the easy one. Now, what did Newton find? Well, he was doing a lot of experiments, mate. And he came up with this. Do you see the big difference? Do you see the big difference? The big difference here is it isn't a straight line. So here we go. Let's not get fazed by that. Let's say velocity is change in displacement with time. Y step over x step. Okay, well, we've got to have 2 points to get a delta. And a delta change between 2 points. Oh, well, that's okay. Let's choose a couple of points there. Okay, so this is a point 416, and the point 864. Let's put those in, 864 and 416. I think you might realise now that what I've plotted here is S of t equals t squared, isn't it? Okay, each x value as is a y the square. Well, that's a nice simple plot that you could get from a motion problem. Okay, what are we going to do? Well, we want to find the delta S on delta t, which is actually the slope of that chord there, isn't it? If we started doing delta S on delta t here, what is this? Delta S is 64 minus 16. Okay, what's your addition like there? What is that? So I think it's about 48, isn't it? Okay, so 48. And we have, oh, no units. What do? We call these meters and seconds maybe. Okay, so there's a change there of 48 metres. Don't watch that. I made a big mistake there in drawing that graph. I haven't put the units in. That's important. And delta t, change in the x step if you like, is 8 take 4, which is 4. So, okay, let's work out this velocity back up here. V equals delta S over delta t, which is 12 meters per second. There you are. We have done it. Easy, isn't it? Okay. Not sure there, are we? Okay, what's going wrong here? Anything going wrong, do you think? I think we should look in here. Uh-oh, there's a gap there. What's that saying? Well, between the points t is 4 and 16 metres and the point 8 seconds and 64 metres, what have we got? We didn't go along that path of the chord. We actually didn't do that. Our motion was not a linear increase straight from this point to this point. What actually happened on this blue line here? This blue line says we actually increased our velocity at an increasing rate. The velocity was changing through that point. It wasn't a straight line situation where there's a constant velocity. No, we had this gap in here. Okay, we did not go straight from this point to this point in a straight line fashion, which would have been a constant velocity through that interval, which would have been this. Oh, V was changing in that interval. Now this was Newton's dilemma. He thought, well, hang on, what is the velocity of the body at an instant in time? Not this average effect. This 12 metres per second is like, hey, that's on the average what happened in that interval. It's equivalent to just going straight like this here. It's equivalent to that. That's the averaging out of the effects. But we actually were changing our velocity in that interval, and it averaged out to 12 metres per second. So his question, what is V inst? What is the instantaneous velocity? And there's the crutch of the Newtonian approach to calculus, differential calculus. What was the instantaneous velocity at various instances along there? Oh, that's a problem. How are we going to do that? So he wanted to say, well, at t is 4, what is velocity? At t is 5, at t is 6, any instant. What is the velocity right at that point? I can't easily take 2 points and do it because I'm going to be looking up here at the average velocity. Oh dear, oh dear. Okay. Do you see Newton's dilemma there? And he went and thought about it. Smart guy. Let's go down and see what he thought. Here we have an idea. Okay. He said, well, if we've just done what we did there, A to point B1 along the curve. So that's called a chord. Right? A straight line joining any 2 points on the curve is called a chord. He said, well, that's an average, but look at the gap. why don't we take it closer? Get points closer. That will have less gap between our straight line and our curve. So B3, B4. Hey, we're getting close, look. We didn't go in a linear fashion between those points, but the gap is small. Smaller gap. It's almost getting close to what we actually did, which was the curve. Actual changes followed that curve in time and displacement. So what did he say? Let's keep it going, let's keep it going, let's keep it going. Let's bring B4 along here. And every time we do, we'll get closer to the actual change in velocity at that instant. Oh, so he said, well, what's the limiting position? If we got closer and closer and closed that gap up, what's the limiting position of a chord? Can you see what he said? Limiting position is, where it's just touching. Limiting position is the tangent position. Okay, and he then defined V inst as the slope, the instantaneous velocity, the slope of the tangent at the point that you're interested in. But here's the problem, the limit, the limiting position. What happens to the slope of that tangent? The slope of the chord as you approach tangent C. Can we find a number for it? It was getting closer and closer to what's really happening. If we could find the limiting value of the slope of the chord, we would have the slope of the tangent. We're trying to find something which the slope of the chord approaches in its numbers. Okay, well, let's go down and look at it a bit more concretely, I suppose, less algebraically. So here we are. He said, well, if we went to the point, let's say t is 5. There it is there. Okay, t is 5. All right. If we want the instantaneous velocity at that point, we don't want a whole lot of chords because they are averaging. We got this gap in here. What we want is we want to bring this along here and draw a tangent. Let's see if I can do it. Let's see if I can draw the tangent to the curve at that point. Okay, so here we go. We're going to do this along there like that and see how we go. Okay, so here we go. There's our tangent at that point. So we've said this is the limiting position of the chord, and its slope will be the limit of the slope of that chord as we go along the curve. Okay, well, let's see if we can measure it. Okay, well, let's do it. This was the point, what is this? This is the point 5, 25. 5 for t, 25. Oh, I've done it again. Have you seen this? Meters and seconds missing. Don't do that. That's bad. Okay, let's take, how are we going to find the slope of this tangent? Well, we've got one point on it. Let's go out to another point. Is there a point that's exactly on it? Well, this one looks pretty good. And this is 855, I think. This point here, 855. So let's work out the slope of that. Okay, the slope of the tangent is y step, which is delta s, or change in displacement with time here. The 55 minus 25 over 8 take 5. Did you get that? Okay, y step on x step in the old days. So this is 30 over 3, which is 10 meters per second. That's interesting. We've done it. I think we've done it. That would be the instantaneous velocity. Instantaneous velocity at t equals 5 seconds. Beauty. We can do it. Hey, that's not bad. Do you have any criticisms of that? What do you think? And I guess you're going to say, Huddy, drawing tangents like that's a bit rough, mate. Don't you think we should do some maths? All right, you wanted it. Here it is. We're going to do some maths. Uh-oh. Here it is. This is what Newton and Leibniz played with. They said, let's take, we'll just take x squared again. We'll go in y and x land because we want a general expression here. So let's take y equals x squared. Well, we just did that with s equals t squared. So now we go to y and x land and come back and look at applications later. So let's take a point, an easy point, point f, which is on the curve. So if x is 1, y would be 1 squared is 1. And what Newton and Leibniz both said, let's imagine moving out from that point along the curve a little bit further. Call it h. So x has gone from 1 along here, h further along. Gone h further along. What's going to happen to the y value? Well, let's look at the formula for the function. Y equals x squared. So if I've gone out to 1 plus h for x, its y value is going to be the square of that, 1 plus h squared. Okay, so that's what they're saying here. We've only moved out a small distance to that point there. Well, you asked for it. I said back on the other screen, drawing a tangent and trying to read off coordinates to estimate its slope is rough. So this is the proper maths to it. So we've got to hang on in there with our algebra bit. Now the slope of the chord is what? Y step on x step. Or I like now delta y on delta x. A bit more sophisticated. Remember, delta means, Greek capital means change in. Okay, so let's do the change in y between those 2 points. What is it? Well, let's just tidy this up a bit. Let's get rid of this. And say the y change is y2 minus y1. There it is. The x change is x2 minus x1. There it is. Okay, let's do some expansions here. 1 plus h squared, first 1 squared, plus twice the product, plus second 1 squared, minus the 1. And in the bottom, the 1's cancel out, you got h. So, our slope is 2h plus h squared on h. Now, that's interesting, but what do we want to do? Uh-oh, let's just do it. They haven't explained it very well here. We want to bring this closer along here to cut out that gap. We want no gap. We want to approach tangent C. So what are you going to do with h? H, the gap between the 2 points, has to tend to naught. Now this is the theory. Instead of drawing a rough tangent like I did, we're going to have a look at the algebra. So let's go down here and say, let's factorise that. H outside of 2 plus h over h. Oh, we can cancel that. And I would like you to put it here, provided that h is not equal to naught. They've got it down here. But the PV proviso that h is not equal to naught, because this step is not legal, of course, if h is 0, can't divide by 0. So here we're saying as h approaches 0, this is the idea of a limit. This is the limiting position. What is the limit of this slope of the chord expression as we approach 0? So what's left is it's approaching the value 2 plus h as h tends to 0. Oh, and what does 2 plus h tend to as h approaches 0? Well, if h goes to 0, this approaches 2. Oh, that's interesting. Okay, so that's the algebra of trying to find the limiting position of the chord and therefore the limiting value of its slope, giving the slope of the tangent. Interesting idea, wasn't it? These two guys both came up with. Okay, let's do it again because I want to do it for the one that we just did and see how good my tangent was. Okay, so s equals t squared from before. Okay, and what did we say? S equals t squared, it was like this, and we were at the point 5 there, and up here, this was s, so this is more Newton's application, 525. Let's go out a little bit, like we just did then. Let's go out to h further on. So this is 5 plus h, and it'll be 5 plus h squared. I'm going to do the same sort of proof as this one over here, only with the number 5, to check that tangent we drew back there. What is the slope of that tangent? Well, let's have a look. There's the chord, and we're going to come along here. So let's start with the slope of the chord. So m is y step 5 plus h squared. Take, what is the other one? 25 over 5 plus h, take 5. Okay, so it's that. And let's expand this. 25 plus 10h plus h squared, take 25 over h. It's all going to be the same math, mate. So let's factorise the top line. 10 plus h over h. That will cancel provided that h is not equal to 0. Now what I want to put in a limit here. We want the slope of the tangent. Okay, that is a limiting value, the limit as h tends to 0 of this thing, 10 plus h. That's what we said down here. What does 10 plus h tend to as h tends to 0? Uh-oh, it's 10. Ah, my tangent wasn't bad, was it? Back on the construction in the last page there. Okay, so the slope of that tangent is 10, because it's what is the limiting value of the slope of the chord as you sneak along back down to that point. Does it approach a value? Interesting to see. The theory is nicely supporting what we estimated with our construction. Remember, construction mathematics is only an estimate. This is proper maths now. This is calculus. And it's good fun. Okay, got the idea? Let's go on a little bit and see what we want to do with it. Well, I've introduced a word, and we're going to pause in calculus land for a minute now and unpack this word, limit. We keep saying, as that chord approaches tangent C, the slope of the tangent will be the limiting value of the slope of the chord. What does the limit mean? A value? It must be a value that the function or the expression approaches, something like that. So let's pause a bit and have a look at functions and what values they approach. And this is important in the IB syllabus because it leads up to a fuller understanding of calculus and what Newton and Leibniz were doing. So let's have a look at a function over here. Put this on the Casio 9860 Plus in graph mode, and the function here, of course, is y equals x squared take 1 divided by x take 1. Let's graph it. Here it is here. Notice anything interesting? Well, I hope you can. Look at that. There's a hole in the function. This function is undefined at x equals 1. There's a hole in it. It's discontinuous. Right? When it's not a smooth curve or it's not a continuous curve, it's called discontinuous. It's undefined at that. Why is that? Well, let's play with it. Let's have a look, because this is interesting, looking at what functions do and the idea of limits. So x squared take 1 can be factored to x plus 1 by x take 1 divided by x take 1. And we're allowed to cancel that, what? Provided that x is not equal to 1, isn't it? Otherwise you're dividing by 0, which is not defined in mathematics. So this function, y equals x squared take 1 over x take 1, is really equal to x plus 1. With one exception. Except at x equals 1, where it is undefined. So, why did I do this with you? Because the idea is a function can have a limit, a value that it approaches, even though it actually never meets it there. Okay, so we say the limit as x tends to 1 of this function is equal to, what's it approaching? 2. because it's going to approach what x plus 1 approaches, and that is at 1, x plus 1 at x equals 1 gives the value 2. And even though there's a hole in it, let's just scribble this out here, there's a hole in it, actually doesn't ever reach 2, but you can make it as close and close as you like to 2 by coming into 1. Either way, if we come in to 1 from here, in other words, come along the x-axis, come down the curve, or come up the curve, we're going to get closer and closer to 2. You just can't have 2 at x is equal to 1 because of this over here. It's undefined when you sub x as 1 in there. So this is a little area of mathematics which is necessary for us to stop and investigate now so that we can fully understand differential calculus. Let's come down and have a look at what we've just done. Okay, here we have the idea. The limit as x tends to 1 of x squared take 1 on x take 1 is 2. Why? Because we've just shown we can make, graphically that was, we can make x squared take 1 over x take 1 as close as we like to 2 by making x sufficiently close to 1. And that's an informal definition of the limit, which is in this course. And we should be able to investigate this mainly. There's not a lot of analytic discussion required for this part of the course. We can do it with a graph like I just showed you on the Casio or whatever graphics display calculator you've got graphically, or we can make up a table of values. We'll come and look at that later, and those two will give us a idea of the limit of the function as we approach a particular point. Okay, I think this one is nice because it shows you that a function can be actually undefined at a point but still have a limit, a value it approaches at that point. Well, that's an interesting bit of mathematics. Some people have trouble getting their head around that. You can't actually ever get to that value, but you can get closer and closer to it. And I think the graph and the table mode shows that clearly, and we'll have a look at that later on. Okay, let's have a look at Pearson's definition now. Some screen clippings from Pearson's here. Just come up here. Alright, limit of a function. If a function f of x becomes arbitrarily close, that means as close as we like. Arbitrarily means it's arbitrary, any value you like to make. Arbitrarily close, as close as we like to a unique finite number L. Well, it was 2 up there, wasn't it? As x approaches c, from either side, that's important. Then the limit of f of x as x approaches c is L. We call L the limit. The notation indicating this is what I've just used back there. It's saying, hey, we know what this function is going to do as you get closer and closer to this interesting x value. And of course, in our calculus, interesting x value will be the x value at the point at which we want to know the slope of the tangent. When a function becomes closer and closer, we say that it converges. Now that word is specifically mentioned in the syllabus, so we must know that. Converges. We saw this before. Refer to sequences and series, didn't we? The what? Geometric sequence and our infinite geometric series, infinite sum. There. If r is less than 1, we tend to sum to infinity. Infinite number of terms tended to a value. Remember that? When we said it converged. Okay, so if you end up getting closer and closer to a value, you say it converged. What's another one? 0.33 recurring is that converges to a third, if you like. Okay, so we're saying a value that a function sequence approaches is said to converge to that value, or that's its limit. Okay, let's have a look at some examples now. Screen clippings from Pearson's here again, and their first example 1. Okay, evaluate x tends to infinity over half to the n by using graphics display calculator to analyse behaviour. because we actually don't have to do a lot of analytic or algebraic discussion of these. Okay, but we know what this does from our exponential work. A half to the x looks like this. This is in graph mode now, and as you see here, it's getting closer and closer to 0. So we would say it's got what? A horizontal asymptote, didn't we? Don't forget that language. That's a link in this course. Horizontal asymptote of y equals 0. Sorry about that. We'll just go back up here. Of y equals 0, or the x-axis. Y tends to 0 as x tends to infinity. Okay, so our limit as x tends to infinity of a half to the n would be 0. Okay, what about doing it in table mode? So if you do go to the Casio and hit table, you've already put the function in graph mode over here, and table and graph share the same window. So if you switch across to table mode, that function that you've got in graph will be sitting there. Then if you hit set, you can set it to go from x is 0 to, let's say, 100 in steps of 1. So then it produces a table here if you hit execute. And you go 0, you can see half to the 0 is 1. Half to the 1 is a half. It's getting smaller, it's getting smaller. Let's scroll down to 20, in which case the number's almost disappeared. This is 9.5 by 10 to the minus 7. Remember this E notation with the graphics display calculator means exponent of 10 is neg 7. So that's a very, very small number. It is approaching 0 quite rapidly there. Okay, so we would then say the limit as x tends to infinity. I know we've used n, x on the calculator, but we've actually used n. So limit as n tends to infinity. What happens if you put an infinitely large n value in there? It's going to be approaching 0. So we say the limit is 0. So we need this to discuss our tangents, because the slope of the tangent is the limiting value, or the limit of the slope of the chord. Okay, let's go along to example 2, and shortly I'll get you to play with some and see what you think. Evaluate the limit as x tends to 0 of sine x on x. You'll say, well, hang on, Addy, when you put x in here, it's undefined at x is equal to 0. But remember the one with a hole in it. That was why I gave you that one. The function need not be actually defined at that point, but still approach a limiting value. Now you can't, and this is what Pearson said here, we're not able to evaluate this limit by direct substitution, because you get 0 on 0, which is undefined. So using a graphics display calculator, so this should have a hole in it here. We should be able to see a hole. It should be discontinuous at that point x is equal to 0, because as we're saying here, it's undefined, but it's still got the limit. So we would say the limit as x tends to 0 of sine x on x equals, what's it approaching? 1. Okay, even though it's not actually defined at that point. Okay, so that notion is important. Alright, let's go down. So that's using graph mode on the calculator. Find the limit as x tends to 0 of 1 on x squared, if it exists. Okay, well, let's have a look at what happens graphically here. If we put in 1 on x squared and x is getting smaller, it has got a, what? Vertical asymptote, hasn't it? Asymptote, a line that the graph approaches in a region. Technically, it doesn't meet it in that region, but I'd want you to be careful with the definition of an asymptote that says it's a line that the graph approaches but never meets. It's not true completely within a region, because you can have functions that do this sort of thing. Okay, so this would be an asymptote in a previous area of the graph. It has cut it. So I prefer the definition, an asymptote is the line or a curve either, that the graph approaches in a particular region. Okay, it may have cut it in another region. So this is a vertical asymptote of x equals 0. In other words, the y-axis, x equals 0. And it's just approaching it. As we tend to naught from above or from below in x-land, this gets huge. 1 over, let's say, what's a small x? X is 1/100th. So y is 1 over 1/100th squared. Invert and multiply, dividing by a fraction, so it's 100 squared. It's huge. So you could also do this in table mode on your calculator, actually subbing values in, like I've done there, to show that it zooms up here. Okay, so therefore we say, come back to Pearson's, you can read that as well. Limit as x tends to 0 of 1 on x squared does not exist. There isn't a limit. There isn't a value L which we can make the function arbitrarily close to, or closer and closer to, as x tends to 0. It takes off. Okay, there's no finite value. Alright, let's come to example 4, and then I'll get you to do some. Now, this algebraic treatment of limits is limited in this course. The course syllabus statement, which I encourage you to read, says that you need to know this basically with technology. Analytical methods won't be required. So this is a bit of analytical stuff here, but let's have a look at it because we do need it for calculus later on. Let's have a look at the limit as x tends to infinity of 5x take 3 on x. So here we have a quotient. So it's too hard to discuss. So what does this mean? It's 5x on x, take 3 on x. So this would then cancel, provided that x is not equal to 0. And so you've got 5, limit as x tends to infinity of 5, take limit as x tends to infinity of 3 on x. Now, because the 5 is a constant, doesn't have any x in it, it's independent of x, it's always 5. So the limit of x tends to infinity of any constant is just a constant. Minus, what does this do as x gets large? Put big ones in there. Put 100, 1,000 in there. It's going to tend to 0. So the answer is 5. This whole dude tends to 5 as x tends to infinity. What about this one up here? P tending to 0. Okay, well there's our expression. Let's take term by term. Okay, so the limit of the whole expression is the limit as p tends to 0 of this bit, and of this bit. Now this is independent of p, there's no p in there. So it's just going to be tending to 3x squared. What's this going to be if you put p as 0 in there? Looking at what this is doing as p tends to 0, it's going to tend to 0. What's this going to do if p tends to 0? It's going to tend to 0. So this function tends to 3x squared. So the limit of a function doesn't have to be an actual value. It could itself be a function. The limit here is itself a function. Okay, so you can have that. Let's have a look at the last one, which is this complicated dude up here, which is very much what we're going to get when we're looking at the limit of the slope of a chord coming into that tangency position. It looks very much like that. So here's our two expressions. Let's expand the first one. First one squared, twice the product, second one squared, minus a 6. And then minus x squared, don't forget this, negative negative makes a plus 6. So we cancel everything out, we get this thing. Now watch this, I like you to put provided that h is not equal to 0 up there when you're doing the cancel. And therefore you want the limit as h tends to 0 of this thing, and limit as h tends to 0 of 2x, well that's independent of h, so 2x is always just going to be 2x if you like, and h tends to 0 will mean that'll wipe out. So this function approaches the value to 2x. I'd like you to confer or compare with the function I spoke of before, this interesting one, where we said this, hang on, we'll just factorise that again. This one had a limit which was x plus 1. Because of that, provided that x is not equal to 1, it approaches x plus 1. So as x tends to 1, this will approach the value 2, but that's the idea of what we're doing here. and we've got a value here of 2x. Alright, okay, want to do some? Let's go down and have a look. There are 11 problems here I want you to work through, mainly focusing on your calculator, and you can use table and graph mode. Should be able to use both. We're interested in studying what happens to the expression for various numbers, and here they're suggesting you put various numbers in and get familiar with it. This is explicitly mentioned in the course, that you should look at actually subbing values in so you get up close and personal with that idea. Okay, so here are the first 10 questions, or 9, you can't read the rest, so I'll scroll those up in a minute. As usual, pause the presentation, have a go, and then what we'll do is come back and look at the fully worked solutions from Pearson's. Okay, let's go down and look at 10 and 11. There's 10 and 11, and really try to understand these functions, because in the next presentation we're going to get on with the calculus of these functions, looking at the tangents and their slopes and the applications, of important applications that Newton and Leibniz both used these ideas for. Okay, let's go down and look at the solutions. So I've kept Pearson's screen clippings here from the TI, and I haven't put in the Casio one. You're going to get too crowded, but you should get a similar sort of thing, a graph and also a table. They don't differ much, the two calculators, in this regard. Okay, so there's an analytical way of doing it, and then checking with the calculator. Analytical way of doing it, and you can check those with the calculator also, but have a look and see what you think. That's question 1 to 4. Okay, question 5, 6 and 7, let's have a look at those. Again, putting in numbers, getting up close and personal with the function, understanding why it's working rather than just see it on the calculator. Okay, and then we'll do 8. I think we can get them all on now. No, 8, 9 and 10. And we'll come and have a look at 11. Okay, and there's 11. Look, I hope you enjoyed this introduction to calculus. Bit of theory there. It's not hard theory to follow though, is it really? Because Newton, if you take Newton's problem, hey, we don't want the gap, mate. It didn't go straight from there to there. It was a different increasing function along here, and we want to look at how it was increasing there. So that's our fundamental idea, and that's not a hard one. So you're into calculus, it's getting into good maths now, so I hope you're enjoying yourself. I'll catch you in the next presentation. Cheers for now.